So it's my great pleasure to introduce Professor Artur Schweidtmann. He's an assistant professor of chemical engineering at TU Delft, where he leads the Process Intelligence Research Group focused on AI, machine learning, and process systems engineering for chemical applications. His research developed advanced algorithms for robotic chemistry, process optimization, surrogate modeling, and molecular property prediction. He holds a master and a PhD degree from Aachen University, complemented by research days at Carnegie Mellon and the University of Cambridge. Professor Schweidtmann, the floor is yours.
Perfect. Yeah, thanks a lot for the kind introduction, kind invitation. It's a great pleasure to be here and also to talk alongside Alexei, Ildefonso, and Ines today. I'd like to talk about a topic that we relatively recently started to work on in our research group, which is about agentic AI for next generation of chemical process design. And this work has been mainly driven by my PhD student, Sophia Ruprecht, as well as Qinghe Gao, with support from Giacomo and Maximilian. And I'd like to start by pointing out the obvious, which is the rise of Gen AI in academia and industry. So over the last few years, we have seen more and more Gen AI use. Gen AI learns essentially patterns and structures from large data set, and it's able to generate new content that's consistent with the learned patterns or data distributions. And in particular, we see a lot of use of large language models, which is a subset of Gen AI trained on large text corpora. But we also know that Gen AI is not limited to text. There's also other data modalities, in particular images and videos, where models have been developed and are also commercially available. If we look at the chemical engineering domain, we see also that Gen AI is actively being researched and used across all the scales. So we see a lot of interest on molecular design, so generation of new molecules, maybe with optimized or targeted properties. This is already ongoing for a long time. Likewise in retrosynthesis, reaction pathway generation, and so on. And then more recently, we see Gen AI in process synthesis, in the engineering and control, supply chain prediction, and also in education. And indeed, our research group has also contributed a lot, especially on the process synthesis and process engineering levels here. But what you see in these works is most of them are monolithic end-to-end black box models. So what I mean by this is, let's take an example from our own research in process engineering, where we, for example, work on predicting PIN-IDs from PFDs. So piping instrumentation diagrams, generation essentially based on process flow sheets. In this monolithic end-to-end black box models, what we try to do is we try to learn this in one step. So one model is going to generate the whole PIN-ID flow sheet. Likewise, in molecular design, we see that a lot of these models take some kind of input, and then they try to generate a whole molecular structure in one step. And this is a promising approach, but there's also a few limitations to it. In particular, these approaches are prone to hallucinations and errors. So in the context of PIN-IDs, for example, you can imagine that PIN-ID is extremely complex. So if you look at a big chemical process flow sheet, a big PIN-ID, well, there's a lot of details you need to pay attention to. And you can easily mess up the whole flow by just making small errors here and there. So if you try to solve the problem in one step, you're prone to build in these small errors and you're prone to adding hallucinations. There's little explainability, traceability, because you try to do it in one step. And they require large and specialized data sets, which are often not available in this setup. And they don't have the ability to correct themselves or reflect on their own outputs. And this contradicts a bit with the workflows that we see in engineering today. So if we look at the actual engineering workflows, for example, in process design, We know that these are structured decision processes and not single predictions, right? So if we ask a chemical process engineer to design a chemical process, he or she is not going to, go to their office and in one step design the whole thing and return to you the ready P&ID. It's rather an iterative process. It spans multiple scales. We need to balance multiple objectives usually. We need to use specialized tools that include simulators, solvers, databases. There's heterogeneous data sources, like Ildefonso pointed out, different data representations we need to work with. And of course, there's the engineering constraints, the safety constraints, the physical constraints we need to satisfy. So the big question is, well, if engineering at the moment is not a single prediction step, how should an AI system be designed to actually support our current complex engineering workflows? And this is where the idea of multi-agent systems comes in. So multi-agent systems consist of multiple interacting agents that coordinate to achieve an individual or collective goal. Yeah. So this is a rather dry definition. So let me use an analogy between agents and engineers to explain in particular what large language model powered agents are, or agentic systems are. So what is an agent and what makes a great agent? I'm sure everyone has a good idea of what a good agent is. One example is James Bond. And if you look at it, James Bond as an agent is driven to solve a goal or an objective. And that's to stop a criminal mastermind threatening some kind of global security problem, right? And then the agent has also access to a number of tools that might be a nice car, secure communication, and so on. And if we take this idea of an agent working to solve a goal with tools in the chemical engineering domain, well, I think we're all good agents, right? So we also have our goals. Maybe we want to optimize a chemical separation process to improve efficiency. And we also use tools in order to achieve our goals. So that could be process simulators, chemical property databases, or engineering documentation. And if we talk about multi-agent system or agentic AI, there's not only human agents, there's also the AI component. So what is an AI agent? Well, an AI agent could be represented through a large language model, could be represented to small large language models that are trained on our domain or specific subdomains. These can also be rule-based systems or deterministic programs, like, for example, some kind of knowledge base that you query. Agents have a goal. In the context of large language models, usually defined through some kind of system prompt. And agents can also have access to tools through APIs, model context protocols. And through these, they can also access databases. They can execute code in coding environments. And they can also communicate with external APIs through the internet, for example. So now that we have an idea of what agents are, the question is, what is an agentic system? So this is basically putting many agents together and letting them work together to achieve a joint or individual goals, right? And we do that already in engineering, and we call it an engineering team. And that's based on human interaction. So it's teams that collaborate, iteratively negotiate, and jointly design, for example, chemical processes. And in multi-agent systems, we try to mimic this with a collaboration between human and AI agents, which can exchange messages, they can use tools, they can query databases and interact. And this is not completely new. This is actually technology that has been advanced in different fields and is also used already in practice. So one example in software engineering is a tool called Devin. So that's an autonomous agent system performing complex software engineering tasks. And it breaks down these tasks into a planning task, writing and debugging computational code, running, executing programs, using development tools, for example, running unit tests or committing code to a Git environment, and iterating until the task is solved, right? And these tools you, in many cases, as a user, interact with through chat interfaces and through the artifacts that are being generated, so the code. An example is shown here, where the user wants to migrate a given code repository from one programming language to another. Right? Another example, a bit more close to our domain, is Agentic, which is a multi-agent system in the computational chemistry or quantum chemistry domain. Also here, we have a lot of agents that are organized by scientific expertise in a semi-hierarchical architecture, and also they share access to tools, including DFT calculations or Python tools. If we now look into the chemical engineering domain, so our domain, we see that there's also a number or handful of multi-agent systems, mostly LLM supported, that have been recently developed and proposed in the scientific literature. Most of them also support some kind of tool calls. Some of them support human integration, and they're built on different frameworks. So the point here is that in our field, there are early works. They are promising, but still it's not broadly adopted. There's still not one big system that's being used. They are all specialized for some applications. So for example, some of these papers specifically target agentic interaction between a user and a specific simulation environment like Aspen+, for example. So what we work on, what we propose is a multi-agent system for chemical engineering that is basically integrating across all the scales. And that is integrating also communication with humans. So we want the system to be human-centric and has access to our domain-specific tools, data, and modalities. So that can be on a molecular level, reaction networks, lab books, can be kinetic data, property data, design heuristics, sensor data, HAZOPs, PIN IDs, so all the engineering data, so where we work a lot on actually up to the economic, environmental, or global level or supply chains, essentially. And what my PhD student is currently working on, Sophia and Chingre, is an initial research question, which is, can we design a multi-agent system that can support separation process design? And what she's been doing is she's following this procedure, which is, first of all, thinking about and designing a multi-agent system architecture. And this is largely inspired by what we as human engineers do at the moment. So what is a classical approach to solve these kind of problems? As part of this, identify relevant engineering tools and databases. So also here thinking about what's currently being used. What does an engineer need in order to solve this problem? Select agentic framework to implement this, implement the framework, evaluate the performance on actual case studies. So what I'm showing you today is work in progress. We are about to publish stuff soon, but it's still under investigation. So let's get started. What we start with is a hierarchical multi-agent architecture for separation process design. And this architecture we implemented in LangChain, which is an open source framework for agentic AI. And usually we start with a start node, which basically symbolizes a user interacting with the system. So a user starts to interact with the system by putting in a request, a written request usually, and that goes to a conversation manager. And the conversation manager has an idea of what's going on, what can I do, what does the system look like, and can negotiate between different agents in the system. And then what we did is we designed a number of expert agents, for example, selecting thermodynamic models, determining phases of a system, retrieving properties, chemical properties. What you can do as well is you can also design sub-networks. So you can have another sub-manager, in this case, a separation system sub-manager, which then again communicates with within its network. So here we have binary separation expert agents and multi-component separation expert agents. So what you see here is basically the manager-expert communication, but the agent can also communicate with one another. So for example, the multi-component separation agent might need chemical properties, and it doesn't need to go back to the manager to ask for that property. It can also directly, ask the other agent, the other expert. And in order for the experts to do their job, they also need access to tools and databases. And we always have a human in the loop as well when necessary, right? So the human can observe the whole conversation flow through the network, also needs to confirm external tool calls, and can correct the agents or interfere in the communication at any time, essentially. And after the problem is solved, well, that's the end node. That's where the conversation is being stopped by the conversation manager. What I want to do now is I want to go through these different agents and just explain a bit what's going on, right? So we have this manager agent. The goal of the manager agent is to coordinate specialized agents to solve the user's request. And the specific tasks include managing, moderating conversation flows, assigning tasks based on the specific agent's expertises, ask the human user for feedback or additional input when that is needed, formulate the final response to the user after all the internal communication is done, and also filter out of scope requests. So if we ask our system here to, write a poem for Mother's Day, well, the manager will reply right away, hey, this is out of scope. This is not our main expertise. Then we have the thermodynamic selection agent. The goal is to suggest suitable thermodynamic models for a given system. Also, in particular, we want to analyze the characteristics of the system, recommend a suitable model based on predefined rules. And we do that through a tool access. So we've implemented a Python-based rule inference algorithm here, and we've coupled that to a knowledge base based on, in this case, prior publication by Carlson. And what you see here on the right-hand side is just an example on how this decision tree, what's basically behind looks like, right? So we go through this decision tree step by step in order to recommend suitable thermodynamic models for a given system. Then we have a phase determination agent. The goal is to determine the phase equilibrium for a given system. So in particular, perform flash calculations, determine phase compositions and their fractions, handle pure multi-component mixtures, also support VLE or VLLE mixtures in our case. And how this is done is, well, we have an agent that is able to perform tool calls. In particular, we use the thermo package, which is a Python package for equilibrium calculations, essentially implemented in Python, and that supports some of the common thermodynamic property models, not all of them. Well, you see, for most of this, we need properties. So we also need to retrieve these properties, and we have an agent for that, which is basically the chemical property agents, or a number of agents, which is when we want to be precise. The goal of them is to retrieve relevant thermodynamic or thermophysical properties for both mixtures and pure components. So identify what properties are required, query databases, software packages in order to retrieve them. And our goal here is to retrieve over 30 relevant properties. And how we do it through a number of tools, tool calls, and different sources. So that includes thermo package again, includes databases like PubChem, NIST, and also if we don't find data in databases, the agent can also run machine learning models like this HANA or GRAPPA in order to predict pure component vapor pressures or activity coefficients, for example. And we also have a model or an agent with the goal to actually recommend suitable distillation-based separation methods. So the task is to analyze feed composition, separation requirements, evaluate potential constraints and operating conditions, and screen and rank conventional and intensified separation column configurations in this setup. And again, we have a heuristic system, basically a rule-based system that's based on recent literature by Lee et al. This is a contribution here from TU Delft from the group of Tony Kiss. And what's actually behind is first of all, an algorithm to retrieve information about the system and the separation task. And then there exist post-identification decision metrics that Lee et al. Developed, which basically recommends whether certain separation columns are suitable or not suitable for a given task. So that includes conventional distillation, heat pump-assisted distillation, heat-integrated distillation, cyclic distillation, membrane-assisted distillation, and so on. And this is, again, formulated as a tool call, integrated into the agent, so the agent can actually make a recommendation based on this engineering knowledge. Okay, let's look at 1-2 examples, case studies. We can start very simple by property retrieval. So what is the critical temperature and critical pressure of CO2? Well, we know for a fact the ground truth. And we have also benchmark, which is what happens if you ask ChatGPT out of the box, right? If you just go to the internet, go to ChatGPT and just ask ChatGPT, and you will figure out that, well, ChatGPT is actually correct in this case. You can also go through our multi-agent system, and our multi-agent system also delivers the correct answer. What's the difference? Well, ChatGPT is a large language model, essentially, so GPT 5.2 we create here, which essentially remembers these values from data, while in the multi-agent system, we have a tool call behind that's actually doing a database retrieval from this and also providing the source for this. But both provide the correct answer here. In the second case study, we want to determine the phases. So we have a given mixture, methane, ethane, nitrogen, with given concentrations at a given temperature and pressure. And we want to know how many phases are there and whether they're compositions. Again, we can do the flash calculations. We can calculate the ground truth. And we can also query this question to ChatGPT. And we see if you use the free online version, well, it gives you a relatively imprecise answer. And that's to be expected. If you, on the other hand, ask our system, what happens is the thermodynamic property models are actually selected, and the flash calculations are actually executed in the back. And then you get the actual result with sources on why this happened. All right, we have one more case study that I'd like to share, which is a bit more comprehensive one, where we have a binary mixture with given compositions, flow rates, and so on. And we have a target separation task, essentially, with given purities and overall recovery we want to achieve. And the task is that we want to select an optimal separation method to split this mixture. And what I share with you here is a video that shows basically the communication between the human and the multi-agent system, and also walks you through what's happening in the background in terms of the AI tool calls here. So let me run the video. This is just a user interface you see with a short introduction, README. And you can start to interact with the chat interface, checking, for example, with whom are you talking? Well, you talk to the conversation manager. This is to be expected because that was the first node you saw in the architecture as well. Then we here copy-paste the query, the separation task that I showed you on the previous slide. And then it takes a bit of time. And let me stop the video for a second because it goes too quick otherwise. So what are we seeing here? what we see is switching to agent separation submanager agent. So basically what happens is the manager recognizes, hey, we're talking about a separation task here. So I should delegate this problem to the separation subnetwork and to its manager. And this manager is rephrasing the problem a bit. And then recognizing, hey, that's a binary problem, binary separation problem. So it's asking its expert agent for binary distillation, binary separation. And we can continue the video maybe. What you see is here the conversation that the human can see, but that's basically a conversation between the agents. The binary separation agent now recognizes that it needs physical properties for the components in order to proceed. And it's changing, or it's, basically asking the chemical property retrieval agent or expert. And this is now formulating a request for an external tool or database. And you can see here also the argument, so the JSON of the tool call. And the user needs to confirm that the tool should be called, because it can be an external call to website. So we wanted the user to basically confirm that. This is running, taking a bit of time for the first component. This is now the second component. See already it basically formulates a structured request that is then sent to an external API or multiple APIs here. You see already the cast number has been identified through PubChem, I believe. And we see here the results of the property retrieval. You see different sources. So from NIST, for example, with critical temperatures, critical pressures. We have information from thermal package, Flashpoint, PubChem. So different sources, information from different sources is now aggregated here, essentially. That goes back to the binary separation agent. That is now calling its own tool. The tool is select binary separation method. And this is this heuristic support system for selection, basically, and for ranking different separation methods. This tool also gives you the result in a machine-readable format, a JSON format. And then let me stop the video here again. And you see the results here, which is shown here. Well, based on the research, based on the tools, this binary separation agent says, hey, this could be a cyclic distillation. HIDIC, I need to check, sorry, that's a heat integrated distillation. HPAD, that's abbreviation for heat pump assisted distillation, and conventional distillation, and gives you a score for those as well. And that's an internal score we calculate for recommending what's the most suitable method. Let me continue. And then this final information is given to the conversation manager, who returns that to the user again. All right. So what I've shown you today is that we build a separation, a multi-agent system supporting separation process design. The multi-agent system is traceable, transparent, and human integrated. However, it's work in progress. So we need additional tools, we need to expand the scope, and we particularly need to systematically validate the results. I believe we will see more of these multi-agent systems in chemical engineering, also for process design. But there is still a lot of research we need to do, and there are a lot of research questions we need to answer, some of which are around the architecture we need to choose. So it's unclear what's the best multi-agent architecture in order to solve our engineering problems. It's unclear how to best integrate engineering knowledge. There's a lot of works around it, but there's still a lot of research that we need to do. It's a bit unclear whether we will see chemical engineering foundation models like the one from Ildefonso, or if it will go more towards large language models. And of course, we need to work on transparency, safety, responsible development in order to deploy those models actually. With that, I'd like to thank you very much for your attention and happy to answer your questions.